Hi there, it's Matteo here. Try and close your eyes and just imagine a world in which the dinosaurs never went extinct. Hey, didn't I say eyes closed? Forget it. Now, this alternative universe is not a bed of roses. Sure, they may have survived once, but the Dinosaur Council isn't fancy about risking a total wipe done once more. So, here enters Bronto. Aww, ain't he cute? Anyways, other than being awfully cute, he actually came up with a solution to prevent future meteor strikes. How about they just made a giant flashlight? Now, I can imagine the confused look on your face. But maybe Bronto knows something we don't. So, can light move objects? Okay, this sounds crazy, so let's take it step by step. First of all, what is light exactly? The way I want you to think about it is that light is made up of funny particles we'll call photons. When I say particles, I want you to think about balls. Why balls? Well, they have a mass, they move around, and they interact with other things, which is essentially what particles do. Now, in physics, we like to talk about mass and movement with one concept: momentum. But what is momentum? The way I like to think about momentum is how much of a mess does something make when it crashes into something else? Then, intuitively, if something is very heavy or going very fast, then of course it's gonna make a big old mess. Now, photons are very special particles. First of all, they go insanely fast. To give you a reference, they can travel from the Earth all the way up to the Moon in just over 1 second. The other funny thing is that photons are actually massless, meaning you wouldn't be able to weight them. Let's stop 1 second and think about the implications of these properties. How much momentum do photons carry? 0? A lot? Something in the middle? The answer is not really straightforward. Being massless, their momentum is actually just a consequence of them carrying energy at very high speeds. Luckily for us, this thing I've just said is pretty much meaningless, and we can just keep on thinking of photons as lightweight, ultra-fast particles. Nothing more, nothing less. Cool, so now we know what light is. We point our flashlight at our meteorite, shoot, and what now? I don't know. Perhaps it's wise we first understand what a meteorite is, right? Meteorites are made of matter, like almost everything around you. So really, the question should be, what is matter? The nice thing about matter is that it's always made up of tiny particles we call atoms. And each atom is also made up of protons, neutrons, and electrons. Now, we can think of the electrons as little planets orbiting around a central mass of protons and neutrons that we call the nucleus. Even better, we can actually just think of these orbits as fixed rails, with the electrons moving on them like miniature trains. Now, how do the electrons decide on which rails to go on? At this point, I probably have to spill you the tea. Nature is lazy. And by lazy, I mean really lazy. Oh, and yeah, by lazy, I obviously mean that it will prefer to keep energy as low as possible. Now, since in our case, energy increases with the distance from the nucleus, electrons naturally prefer to stay close to it. This is what we call the ground state of the atom. Luckily, things aren't always that boring. Let's try and live life as an electron. You wake up, you have tons of energy, and you really want to do something crazy. For electrons, this means going from an inner orbit to an outer one. This is the excited state of the atom. I kid you not, that's actually the proper name for it. So instead of doing the lazy route, the electrons ride the wild roller coasters that are further away from the nucleus. But why don't they always do this? Well, to do crazy stuff, you need energy. For me, this means that you need a good breakfast. And no, I'm not British, this was just the easiest thing to draw. Now, you may be asking, what's breakfast for electrons? Well, photons, of course. If the photons are tasty, electrons get the extra energy they need and they reach the excited state. But sometimes breakfast isn't that great. The electrons eat the photons, think about it for a bit, and then spit them out. No food, no energy, no excited state. Cool, so now we know light and we know matter. But what about light and matter getting together? We have two possibilities. The first one is that the photon comes in with some momentum, gets absorbed, and the momentum is transferred to the electron. Whereas if the photon is reflected, the electron experiences a recoil twice as strong as the initial momentum of the photon. Then, in both cases, the electron receives a momentum kick. So we didn't actually care what interaction was happening in the first place. In fact, there's probably many other things happening, but it's not important anyways. Now, since the electrons are bonded to the atom and atoms are bonded together to make the meteorite, the momentum kick actually just transfers to the whole meteorite. So that's how we stop it. Photons hit atoms, the atoms move, and the whole meteorite slows down. This seems to check out, but I'm sure by now some of you will have figured that this isn't a very effective method. I mean, you don't really feel pushed down by sunlight, do you? To get the desired outcome, we'd need roughly 10 to the 29 flashlights. And yeah, that's quite a lot. To put it into context, if you'd manage to get all of the sun's light to hit the meteorite, you'd still need 1,000 suns. Not really doable, huh? To be honest though, Bronto's idea isn't all that stupid. Scientists have been working on solar sails capable of using the sun's light to push little space objects around. It still sounds like science fiction, but hey, hopefully now it feels less magic and more just physics. This was all from my side. Stay curious! Oh, and for the extra curious, this is how I got all the estimates. Don't forget to follow!